Hi there. In this video series, what we're doing is building up towards the Fourier transform. What we've done so far is that we've taken the Fourier series and converted it into a polar form that uses complex numbers. So the Fourier series that we've converted into this complex form looks something like what we've derived in the previous videos. That's ft, some function of t, is equal to a sum that starts from minus infinity to infinity of some coefficient Cn times e to the power jn omega t. And we've also explained what this omega is, we explained what frequency is, and all of these things are going to be relevant in the upcoming videos. And we saw that this coefficient Cn is equal to the integral from 0 to the period t of f of t multiplied by e to the power minus jn omega t. And of course, this is an integral, and we're integrating with respect to dt, and this whole thing is multiplied by 1 over t. So please go and look at the first video if you can't remember how this comes about. So what we're going to do now in the next step towards building towards the Fourier transform is that we're going to talk about discrete spectra, because this is a preliminary in order to understand the Fourier transform. We look at the discrete case first, and then we extrapolate it to the continuous case, or we use the discrete case to develop the continuous case. And the continuous case is actually the Fourier transform that people know and people use. But we have to understand this part in order to get there. So the best way to illustrate discrete spectra is through the use of an example. So what we're going to do is write this Fourier series for this function f of t, okay? And we're going to determine this coefficient Cn. So this coefficient Cn is a constant of great importance in this particular video. So this is the example that we're going to look at. We're saying that f of t is equal to 0, and then it's equal to 1. And from 0 to a, it actually takes on the value 1. Okay, sorry, I've made an error. It takes on the value 1. And then from from a to t, this is the period t, it takes on the value 0. So if we look at the graph of this from 0 to a, it takes on the value 1, and then from a to t, it takes on the value 0. And of course, this is a periodic function, so we're saying that after some period t, the function just repeats itself. So what we're now going to do is write the Fourier series in this polar form and determine this coefficient Cn, which is quite important for this kind of example. And then we'll talk about the spectra and what it means thereafter. So the first thing that we need to do is determine this coefficient, and we have written the equation for it, the formula for it. It's just 1 over t times the integral from 0 to t, f of t, and so on. So c of n is equal to 1 over t times the integral. Okay, we'll write it like this. It's the integral, firstly, 0 to t is broken up from 0 to a, and then a to t. So we are going to integrate from 0 to a. And from 0 to a, the function value is just 1. Okay, so we just have 1 times e to the power minus jn omega t. We have e to the minus jn omega t dt. Then the next part of the integral is from a to t. And of course, the function value is 0. 0 times e to the minus jn omega t dt. So since this is 0, this entire integral is just going to be 0. So what we're left with is just 1 over t times the integral 0 to a e to the power minus jn omega t. So this is a simple integral to evaluate. All we are just integrating is the exponential function. We have 1 over t, and we integrate it. We're going to have the integral of the exponential function is just the exponential function. So we're going to have e to the minus jn omega t as the integral. And of course, we'll have to divide by minus jn omega, because we have to account for this factor, or this number being as part of the variable. And we're integrating from 0 to a. So we do this substitution. So we have substitute in a in place of t. And when we do that, we have e to the power minus jn omega a, and minus, Okay, and when we substitute in 0, we have e to the power 0. So anything to the power 0 is 1. And then we're dividing that by minus j n omega t. What we're going to do now is we're going to use some of the knowledge from the previous video in which we said that the angular velocity is equal to 2 pi over t. Okay, so what we're going to do is just get rid of this t in the denominator here. So t is actually equal to, or rather we have omega t, so we can just say, omega t. So omega t is equal to 2 pi. So we're just going to replace this omega t in the denominator with 2 pi. We can just do that here. We'll just have minus j times n, we can just put the 2 here, times 2 times n times pi. We just substituted that in. So the next thing that we're going to do is we're going to take e to the minus j n omega a as a common factor, okay? Or rather, minus j n omega a over 2 as a common factor. So minus j n omega a over 2. So we've pulled that out as a common factor. So we have to ask ourselves, e to the power minus j n omega a over 2 multiplied by what will give us e to the minus gen a omega a? And the answer to that question is simply e to the minus j n omega a over 2. It's literally the same thing because we can think about it as minus a half gives us minus 1. So we have minus 1 in this exponent. So minus a half gives us minus 1. And also now this e to the minus j n omega a over 2 multiplied by what should give us minus 1. Remember that anything to the power 0 actually gives us 1. So what we have to do is multiply it by minus e to the power j n omega a over 2. Notice that this exponent is positive. So we have minus 1 analogously, minus 1, then plus 1, minus 1 plus 1 gives us 0, and then e to the power 0 gives us 1. So that's how we got that there. And of course, we have to divide by this denominator. So this entire thing is divided by minus j times 2n pi. So what we have is something very interesting looking. If we now just get rid of this minus, so we'll just get rid of this minus first. So what we'll do is we'll just divide by minus 1. So if we do that, then what we get is everything reverses itself. So this will go here and that will go there. So that becomes a positive and that becomes a negative. So if we look at this term, it looks very familiar. It looks like something that we have actually done in previous videos. And in the first video specifically, we showed that sine x, or rather sine theta is equal to e to the power j theta minus e to the power minus j theta divided by 2j. Well, this term is actually sine theta, okay? So if you look at what we have here, we have e to the power something, okay? Then minus e to the power minus something, and then we have a 2j, which corresponds to the 2j there. So we can replace this entire term with sine theta, or rather sine of that angle. So that's what we're going to do. If we do that, what we're left with is e to the power minus j n pi a over t. Okay, so what we've done here is we've taken this omega and replaced it to be in terms of the period. So omega is equal to 2 pi over t. So that's what we've done. Obviously, 2 times half is going to give us 1. So we just have pi a over t. Then substituting the rest in, we can do the same here. So this angle is j n omega a over 2. We substitute this omega to be 2 pi over t. And what we're left with is sine of the angle. Let me just bring this down. sine of n pi a over t. And we're dividing by what's left, n pi. We can see that we have sine of something, and in this denominator we have kind of something that looks or is from the angle itself. There's an n pi in the angle and there's n pi in the denominator. So sine x over x is something that's very commonly occurring in a lot of different equations, commonly occurring in nature or wherever else. So we would just want to put this expression that we derived to be in terms of sine of the angle divided by the angle. So the only thing that's missing in the denominator is this a over t. So we can multiply the denominator by a over t. So since we have multiplied the denominator by a over t, we also have to multiply the numerator by a over t. And when we do that, we just put the a over t there. So that's what it looks like. So there's a reason why we have put it to be in terms of sine x over x, or sine of the angle divided by the angle. And we'll analyze that just now. So this is what Cn is equal to. And we can write the Fourier series like this, right? So all we just do is we take this expression here. This is what Cn is. Okay? And we substitute Cn inside here, and we just multiply this by e to the power j n omega t. And we can write an expression, a longish expression for the function expressed as the Fourier series in this form. But what we're actually going to do now is just do some analysis on this coefficient Cn. So this Cn is actually called the spectral coefficient. So what we do is we take this spectral coefficient Cn and we split it into two parts, okay? So we write it as Cn is equal to this magnitude of Cn multiplied by e to the power j phi n, okay? So if we look at this expression that we've just derived, okay, we can show that it's actually of this form. So this first part that I've written, absolute value of Cn, okay, what this is actually equal to is this part of the expression. So that's a over t multiplied by sine of, okay, let's write it like this, sine of n pi a over t divided by n pi a over t. Okay? This particular thing is called the amplitude spectrum value. That's the amplitude spectrum value. So the next part of this coefficient Cn is this e to the power j phi n. So there's our e here, and we have our j here, and then this phi n is actually equal to minus n pi a over t. So phi n is equal to minus n pi a divided by t. So this phi n is called the phase angle. In this case, it's the phase spectrum value. That's phase spectrum. So what's the significance of this? But before we explain the significance of this and how this is all building towards the Fourier transform, perhaps we should just quickly remember what phase actually means. Phase actually indicates the extent to which an angle is delayed. We could have a signal sine theta, or sine of t rather, or let's just say theta. Sine theta, and if we remember sine theta, it looks something like that, okay? Starts off at 0, and it hits that peak there at pi over 2. Sine of 90 is 1. So if we were to just write sine of theta plus pi over 2, so what does that do to this signal? What it does is that it starts off the signal at a higher value. So instead of starting like that, it starts like that. It starts off at 1. Okay, because 0 plus pi over 2 is pi over 2, and pi over 2 is 1. So it's the same thing as cos theta. So this is the same as cos theta. So that's what the phase angle is. It basically indicates the extent to which how the signal starts, basically. At what point does the signal begin? So if we speak about something being in phase and being out of phase, if this phi n is basically equal to 0, then what it means is that if we write a signal and they have this amplitude spectrum value, it means that for each signal that we create with a value n, it means that all of those signals will be in phase, or they would all basically start in the exact same way. So what we're going to do to understand the significance of this amplitude spectrum and the phase spectrum in the context of this example is we're just going to plot the amplitude spectrum. So what we're going to do is we're going to have, on the x-axis we'll have time, and in the y-axis we'll basically have the amplitude spectrum value. Okay? So if we plot this expression here, what would we get? Well, we can substitute different values of a and of n, and then we can plot it like that. But we can show that what it's actually going to look like is something like this. Remember that we're doing it for different values of n. So because we're doing it for different values of n, it means that we're going to have different values plotted here. So if we plot n is equal to 0, okay, so this n is equal to 0, what we're going to have is this value like this. And then if we plot n is equal to 1, okay, maybe we're going to have something like that. We're going to have a different value lower down. And this would correspond to na over t. Sorry, pi a over t. That's pi a over t. Pi a over t, which corresponds to n is equal to 1. So we carry on like that. We can even plot n is equal to minus 1. So if we plot n is equal to minus 1, we get that. If we carry on doing this for different values of n, we get another value there. We get another value after that like that. So each of these different values of n will give us something like that. And then we would reach, for some n, where this amplitude spectrum value is equal to 0. And then once we go beyond that point, we find it giving us the same thing. But we can see that this peak is lower. So this is just what it would look like if we carry on plotting it. And then it would repeat itself, but again, this y value would be lower, this peak would be lower. So we have one big peak like that. Okay? These are all discrete values. If we just wanted to put a dotted line through it, just to indicate that this is discrete values, then we can see that we have one long lobe like this, and then we have smaller lobes like this. So what is this actually telling us? It's telling us that we have different amplitude values that correspond for different values of n. So different amplitudes mean different signals. So we are taking, in other words, a whole bunch of signals with different values of n. So each value of n actually corresponds to a different signal. So that's one signal, that's another signal, that's another signal. And remember, this is an amplitude, okay? So there's the angle, and that's the amplitude of that, essentially. So all of these signals adding together, right, is going to give us this original function for which we had done all of these things. So this is the example that we had considered. So we have done this example. We have taken this coefficient Cn, we have broken it up into two parts. And we saw that when we split it into two parts, okay, we have a signal, okay? And the amplitude of the signal can be represented by this absolute value of Cn. And then when we plot it, it looks something like this, okay? We have one big lobe, and then we have smaller lobes like this, okay? So that's the whole significance of this. If we take each of these amplitudes and create signals out of these amplitudes, then we'll sum them together and get this original function. That's the idea. We can see that it hits 0 at this point, at these different points. So what that is actually telling us is that these particular angles, they don't really add anything. They don't mean anything in terms of what we're trying to do in terms of breaking down some kind of function into individual signals, discrete signals, that is. So we can see that the majority of our function can actually be obtained within this first lobe. the reason why we have all these additional lobes, and it would carry on going on, getting much smaller and smaller and smaller, is because of these sharp edges, okay? You can see that we have a very sharp edge here, and then we have a very sharp edge here. So if we're saying that this function is a sum of signals, okay, then we're saying that to get the sharp edge, we have to sum up a whole lot of different signals. So that's why it needs to converge into this sharp downward pointy end like that, and even here as well. So we get this sharp edge like this by all these smaller lobes. So that's the key understanding behind this. So we can also plot this phase spectrum. We can do it down below here. We can also plot this phase spectrum. So if we plot this phase spectrum for different values of n, and on the y-axis we have phi n, sorry, not beta. So when n is equal to 0, okay, then we have no phase angle, okay? We have phi n equal to 0. That means that all of the signals that we would develop would all be in phase. They would all start in the exact same, or at position 0, they would all have the same value, essentially. Well, not the same value, but they would be in phase. They would be superimposed. So since we have a phase angle that's dependent on the value n, for different values of n, we could say n is equal to 1, n is equal to 2, n is equal to 3, then n is equal to -1, -2, -3. We're going to get different values of phi n like this. Remember that these are discrete points. So it'll probably look something like that, okay? So in order for us to develop the signals for which the sum of which will give us our original function, we need to know the amplitude and we need to know the phase, okay? So the amplitude tells us where essentially a signal would be in terms of height and how big it looks, okay? So this amplitude of the signal is essentially we get from this amplitude spectrum. And where the signal actually starts actually is told to us by the phase angle. So if it's, maybe if n is equal to 1, maybe it might start like that. Okay, so a sum of all different signals in which we get the amplitude and the phase by actually looking at these different spectrums. So what is the point of this in terms of the Fourier transform? How is this going to help us understand the Fourier transform? So this is the case for a discrete function, okay? So what we've done inadvertently is looked at the discrete form of the Fourier transform. The Fourier transform essentially does the exact same thing as this. We take some kind of function, it'd be a continuous function, or whatever is the case. When we extend this to a continuous thing, what happens is that this, instead of becoming time, it becomes frequency, okay? And remember that we interchangeably use the word angular velocity with frequency, but in any case, this time becomes frequency, and we plot it, and it looks something like this. And this is no longer discrete values, it's a continuous curve, so we can draw a line through it. But that is the subject of the next series of videos, or rather the next video. So what we're going to do in the next video is we're going to take everything that we've done in this example and extend it to the continuous case. And when we extend it to the continuous case, we see how time becomes frequency and how this becomes a smooth curve and how the Fourier series looks up the way it ends up looking. Remember that the whole point of the Fourier series is to take a function and split it up into a sum of different signals. And when we dissect the Fourier transform, we get two different spectrums. We get an amplitude spectrum and a phase spectrum. And these two pieces of information tells us which signals is most applicable and most relevant in terms of summing up to give us our original function. But since this is the discrete case, for now this is time, and this is a discrete series of points. So in the next video, we're going to extend this to the continuous case and derive the Fourier series in the form that you would probably know it to be.